Thank you. I mean, I was 8. I wasn't going to learn any life lessons. So yeah, I'm going to talk to you, finish off this round of talks about Chandra, but I'm not quite sure what I'm going to talk about. So I've given you 3 titles, and you'll decide at the end, I guess, what my talk is actually about. Either this is a mysterious mystery of an undead star that I have tried, and spoiler, thus far failed to solve. Or it's a tale of 3 space telescopes, how using different space telescopes together, we can uncover things that on their own they would never have found. Or it's a cautionary tale of why if someone says to you, there's a mystery that needs solving, you say, not me. So this is how it started. Oh, wrong way. This is how it started. I was 2014. I was a young, fresh-faced grad student, first year looked like this, and my advisor, who's also a Terminator for reasons, 2 officers independently came up with that nickname for him. He said, "Oh, would you like to lead a Hubble Space Telescope program?" I was like, "Oh, wow, how exciting!" And it's on a mystery that is decades old. And I said, "Oh, wow, that's very exciting." And so I said, "Yes. Of course, I will solve the mystery. I will be that one to lead us forward in knowledge, to boldly go where no one had..." No, Star Trek. So what was the mystery? This is a GD394. It's the blue thing in the middle, and it is a white dwarf. So what is a white dwarf? We've seen kind of this track a lot this evening. This is the stellar evolution, so the changes that stars go over during their lifetime. And yeah, we've seen a lot of supernova, seen a lot of really pretty Chandra images. But most stars, over 95% of stars, anything below 8 times the mass of the sun, roughly, goes up this way. So really, we can probably ignore that bit. So the stars, when they reach the end of their lives, they run out of hydrogen fuel in their core. They swell up into a red giant. This is nowhere near to scale. They swell up to huge sizes. So the sun will swell up to the size of the Earth's orbit, which is bad for the Earth. And then they'll blow away the outer layers, leaving behind a tiny glowing core that we call a white dwarf. Wrong way again. White dwarf. We have a circle around it. And this is what I looked up close up. So white dwarf, about the size of the Earth, on average, slightly over half the mass of the sun, which means they're very, very dense. So their gravity is 100,000 times the size, the strength of the Earth. So don't fall over on one, I guess. Don't go near one. And GD394, at most wavelengths, in the optical at least, where this image was taken, it just looks like any other white dwarf. About half the mass of the sun, about the size of the Earth. It's about between 30 and 40,000 Kelvin, so it's pretty hot, hasn't been a white dwarf for that long, and it shows signs that it's accreting remnants of its old planetary system. Bits of asteroids are falling into the white dwarf, but that's not particularly unusual for a white dwarf. About a third of them show that. So why, in the astronomical literature, has it got this epithet of mysterious? Well, for that, we have to go for a journey through time and across the electromagnetic spectrum. So you've seen this before. This is the electromagnetic spectrum, all the different forms that light takes depending on its energy. So the visible bit that we can see in the middle, the infrared going out to longer wavelengths, and then the interesting bit, the short wavelength bit, sorry to any infrared astronomers out there, into the ultraviolet and the X-ray. And here are those 3 different telescopes that I was talking about. And to really uncover the mystery of GD394, we need all of them. Starting with this one. We're going back to the mid-90s. So the telescope looks like this. The star is the same picture, look the same. And just for context, I look like this. And this is the Extreme Ultraviolet Explorer, which, as the name suggests, observes in the extreme ultraviolet. Because for some reason we didn't give this one a name, just a description, really. And this looked at GD394 and it saw this. So this is a light curve. So the amount of light coming from the star in the extreme ultraviolet over time. And see, it's got this about day-long periodicity in it. It's getting brighter and dimmer by about 25% every day. And white dwarfs don't usually do that. In fact, they're notoriously stable. They're so stable in brightness that we use them as comparisons. We check against white dwarfs and say, okay, they are not varying, therefore we can see the star next to it varying. And no other white dwarf does this in the extreme ultraviolet. So what's happening? Well, the idea they came up with was based on that idea I mentioned before, that it's accreting bits of asteroid from what used to be its planetary system. And the Dupree et al. Said, well, maybe it's got a spot on it. So instead of that accretion being evenly distributed over the whole surface, magnetic field is drawing down that material onto a spot. And as a spot comes into view, so you can see a spot here and a light curve here. No spot is brighter because there's no dark bit. And then as the dark bit moves on into view, the light curve gets dimmer. It's a good idea. So how do you test this? We're going to far ultraviolet now in 2015. This is the Hubble program. I was going to lead. And this is what happens when you grab an image off Facebook and blow it up onto a big screen. This is me prepared. This is a colander on my head. I was preparing to watch a solar eclipse. Colander and the solar eclipse, really, really good. Like, I was really surprised how good they are. The idea of Hubble is to look at that bits of asteroid falling onto the white dwarf. So this is a spectrum. It's just a light, so wavelength over here going from basically ultraviolet to a bit less ultraviolet-y, and the amount of light. And each of these dips is a characteristic signature left on the spectrum by an element. In this case, silicon, and maybe oxygen in there. And very simply, the deeper the lines are, the more metals you have on the lines. So if we have the idea that all of these metals are in one spot, then as the spot moves in and out of view, the lines should change shape. So we're expecting to see something a bit like this. Time that right. As the spot moves into view, the lines get deeper and then shallower as it goes out of view. That was the prediction. So we asked for time on Hubble Space Telescope to observe it 8 times, timed very carefully so that we'd see different parts of that roughly 1-day period. And our prediction was that the line should vary like this. And I was very excited. I got emails saying Hubble was observing for me. That was probably what I should have told 8-year-old me. It was like, oh yeah, you'll get to use Hubble one day. But instead of this, they look like this. So they ignore the bit changing at the bottom, that's just noise. They were all the same. So where previously I've been very happy having Hubble, I then look like this. So what's going on? There are no changes, and as far as you can tell, and I've checked, it doesn't change at all anywhere apart from this extreme ultraviolet change. Okay, so maybe the spot went away. That would be the easy explanation. However, we've got to do a bit more time travel. We're going back to 1992. If you're beginning to think that this is just a talk about Hubble that I've shoehorned Chandra into the end of, you would be right, but I'm getting to Chandra. So this is Hubble as it looks in. This is when it was launched. You can tell that by the big solar panels that were the original ones built in Britain. Not very good, so they had to be replaced. And Hubble observed it in 1992. And here is the grey is the old spectrum, and the black is the newer one we got in black typo that we got in 2015. And you see the improvement in the quality of the data, but the main result is that it's the same. So if the spot's gone away, and 1992 is close enough to the old Eevee observations that we're pretty sure it must have happened then. Otherwise, it would have been an amazing coincidence for the spot to turn on just as we launched the only telescope that could ever see it. So if the spot's gone away, then it has to have left the spectrum absolutely unchanged. But this is kind of circumstantial evidence that it's gone there. And so I said next, let's double check with Eevee just to be sure. Obviously, if you think it's gone away, check with the thing that saw it in the first place. There's a slight issue with that, in that this is not quite what this is not actually Eevee, but that is exactly what it did in January 2002. Reached the end of its mission, and what was the word? I am old. Did that into the Earth's atmosphere. So we can't use Eevee. Again, it's kind of bits. But what if there was another telescope? Now, there's no other telescope that observes exactly in the same wavelengths as the Eevee, but there is one that overlaps. And you can probably guess by now that it is Chandra. Was someone booing? I mean, those talks are really great. I'd hope you love Chandra by now, but oh well. So we applied. We said to Chandra, this is 2019. We'll look at it in the X-rays of Chandra. This is what the telescope looks like. Stars still look the same. And I look like this. So the idea was, we applied to look at Chandra and just to look at GD394 of Chandra and stare at it straight for a day and a half. Turns out, if you keep it at the same angle for a day and a half, it'll melt. So they said we can't do that. Spoil sports. So we're going to, but it's fine. We rearranged it so we could observe it and make sure we're observing the whole phase just in different sections. Same as we did with Hubble. With Chandra, because it's an improvement on EUV, we can search for structure in the variation and look for, see if the shape of the light curve will tell us what's going on. Is it a spot, or is it something like a cloud passing between us and the white dwarf? Is it even a planet of some sort that's evaporating? We can look for other things. There's many more mysteries around GD394 that I didn't have time to go into, but one of them is we think that bits of planet, the bits of asteroid talked about before, is accreting onto some sort of corona around it, and it's making a plasma that we could see in the X-ray. And could we finally, after many 25-ish years, solve the mystery of GD304? So I would love to be able to show you our Chandra data and have as many pretty pictures as the other two talks. However, last October, Chandra went into a safe mode, which basically meant it stopped and didn't observe anything for a few months, which meant all of the other observations that were planned out had to be moved around a lot, and long story short, February 2019 became February 2020. So I hope you join me next year for the 21st anniversary of Chandra. Thank you very much.
So I feel your pain a little bit as a person who was expected to get some of the first data from the Just Wait Space Telescope this month. For the record, the James Webb Space Telescope, the launch itself got delayed until March of 2021. Boo was right. Anyway,
its original
at least Chandra's in space already.
Yeah, its original launch date was 2007.
Enough of that. All right. Any questions? Not about James Webb, about Chandra. Let's see, right here.
So I don't know anything about this item except that can't be the only theory of why you have this variation that you have a rotated spot. What are the other theories that are?
Yes, the one that we proposed, I finally got a paper out on this. It's a very, I think it's a very good paper, but it's very long and a bit dull. Last year, where we proposed instead of a spot, one way that you could potentially explain it is if you had, and we've seen these other stars, a planet that isn't passing in front of it, but is so close to it, the planet is heating up, evaporating material off it, and the cloud of material is passing between us. And that wouldn't show up in the optical, where we've got really good data that hasn't got a material transiting in front of it, but it would show up in the ultraviolet and potentially cause that variation. I am not so keen about that explanation, but Chandra will actually tell us, because Chandra will be able to see the shape in the light curve, and that cloud passing in front of it has a very distinctive shape compared to just a spot. Yeah.
Any other questions up top? Okay. In the back?
You mentioned one third, one fourth, that they've noticed the planet.
Yes, yeah.
That seems like a high number. Is that one third of what we've observed, or is that just
No, so that is so that's a statistical number. When we look at a white dwarf, it has a roughly 1 in 3 chance of having bits of planet accreting onto it. The actual number of white dwarfs that have planets is probably very close to all of them, because that's where we're getting with main sequence systems, like stars before they're dead. They all seem to have planets, or the vast majority seem to have planets. So it's not unexpected that most of them. And then the ones that we actually have evidence of, we actually need quite a specific situation. We need something to be scattered into the white dwarf and actually hit it, or go near it, and it gets tidally disrupted and then falls onto it. So the actual fraction could be higher. But yeah, about a third is where the observations are, and that's not unexpected. Yeah.
All right. One more over here.
what's your favorite Lego set?
Oh. The Saturn V is very, very good. It's, yes.
All right, on that note, let's thank our last speaker.